In this video, I'll be talking about the field of technical drawing. Technical drawing goes by a lot of names. Common names include drafting, engineering graphics, engineering drawings, computer-aided design, and recently a new area called model-based definition. Humans have been making technical drawings for a long time. This statue, which is about 4,000 years old, shows a guy, maybe an early architect, with an architectural plan on his lap. And this has been dated to over 4,000 years ago. Modern technical drawing really came about by the work of a guy named Gaspard Monge. He was a French mathematician, and he wrote a book called Descriptive Geometry in the late 1700s. And the ideas that he put forward in his book became the basis for the first technical drawing classes taught at universities. Monge's name is actually one of 72 scientists and engineers whose name is included on the Eiffel Tower. So he's in pretty good company. Monge's ideas involved imagining that the views of objects are projected onto planes that lie between the object and the viewer. So in the example here, we see what's called a projection plane. You could imagine this to be a clear sheet of glass between you, and you would be standing over here on this side, and you would be looking in the direction of the object. So this sheet of glass or projection plane is between you and the object that you're trying to visualize. So in Monge's view, what you do is you project the features of this object onto this two-dimensional projection plane. So for example, this plane right here becomes this plane here. The plane in red in the background is this plane, and here we see this hole that's projected onto here. Even has some center lines or center marks on it. And this plane we see right here is this plane. Monge's ideas really became the foundation of modern technical drawing. And so here we see that same part that we saw in the preceding slide, but this time we've added a horizontal projection plane to the top, and we project up to it with from our 3D part, and we get a two-dimensional top view. We place another projection view to the side of this object, and remember, we're standing on this side looking in the direction of the object, and we project the features of the object onto the projection plane. So in this case, we have what's called a profile projection plane, which gives us a side view. So we have a front, a top, and a side view, and this really becomes the foundation for what we call multi-view drawing. In multi-view drawing, we may draw the front, the top, the side, the back, the left side, the bottom. We have a lot of different options of views that we could draw, and then we can add dimensions to those views and notations and other things necessary to make the part. The introduction of personal computers around 1981 and the development of CAD programs that could run on a PC really changed this industry. So we go from a drafting board to a personal computer. And today, sales and licensing of programs like AutoCAD, SolidWorks, Revit, Inventor, Civil 3D, Creo, and there's others, has become a $9 billion a year industry. The workflow in modern CAD programs, though, is increasingly moving away from the creation of 2D line drawings toward the creation of an intelligent 3D model from which the 2D drawings are derived. So in other words, we create a three-dimensional model, and then we just project our views, front, top, side, whatever's needed from the 3D model. We say it's an intelligent 3D model because If we change the shape or size of the 3D model, the projected views change automatically. We don't go in and redraw them two-dimensionally. The newest iteration, though, of technical drawing is called model-based definition. And in this, we derive manufacturing information directly from a 3D model, and there's limited two-dimensional drawing involved. A good example of this is sending information from a 3D model directly to a 3D printer or a CNC machine. Modern technical drawings that use model-based definition may be outputted as 3D PDFs. And so I have an example here. This is actually a screen capture of a three-dimensional PDF. And in the PDF, if you pick on the model and hold down with your mouse, with the pick button of your mouse, and move your mouse, you can actually rotate the model, or you can come down here and click on the thumbnail images that are included right here, and you'll see the multi-views, like the front, the top, the side. You can also run inquiry commands on this, and you can find out the sizes of features and how many that there are, and also fabrication notes and things like that. So maybe the best way to define modern technical drawing is to show you some examples from the different disciplines. So this is an example of an architectural drawing done using Revit, and these are called elevations, and you could think of this as maybe the front, the right, the back, the side view of this building. This is the floor plan of a building that also was created using a 3D model, and the software was called Revit. So the floor plan is derived directly from the 3D model. These are some construction details. This is a wall section over here, and some details where the roof joins to the wall. And these can also be derived directly from a 3D model, or these could be drawn as just 2D line drawings, either one. This was done in Revit, which is the 3D modeler. If you were doing this in 2D, you might do it using AutoCAD. These are also some Revit drawings that show the foundation details for a building, and these were derived from a 3D model using Revit. These drawings are the elevations of a residence that was used on a set of house plans, and these were all drawn using AutoCAD, and they are 2D drawings. So these are not these were not derived from a smart 3D model. These are just true 2D line work right here. Here's the floor plan for a large commercial building, and this was done using Revit. So it's derived from a 3D model. Here are the drawings for what we call MEP, mechanical, electrical, plumbing. And so this is the heating, air conditioning, and ventilation for a building, for one floor of a building. And so we have the level 1 plan and the level 2. So these are like your air conditioner and the ducts that run through and where they come out into the rooms of the building. This is a sample civil drawing of a subdivision showing a road and the lots that are in that subdivision. And we also see some sort of a section view cut through. And so all of this was done using a program called Civil 3D. This is a topographical plan showing the higher parts and the lower parts of a property. And it looks like, so the higher parts back here, this says it's 471 feet above sea level, and it's falling in this direction, and this band across through here is at 463 feet above sea level. So the higher part of this piece of property is over here on this side, and it's sort of falling downhill over here to this side. Now this is important to civil engineers who are trying to direct the flow of water off of a piece of property when they develop it. This is a civil drawing. This was also done with Civil 3D, and it shows a new stretch of road that's going to be manufactured. and or not manufactured but built. And what this shows down here is like a front view of that road, showing that the road is running downhill. And at this point, if we project straight down from here, the road is at its lowest point right here, and then it starts back uphill here. Excuse me. So a civil engineer might use this to decide where to put curbs and where they want the gutters on the sides of the road to collect the rainwater. This is also civil drawing, and this is used to develop, or this example is a corner lot at the intersection of two streets where somebody wants to develop this corner and put in, I believe it's a pharmacy. And so the pharmacy will sit right here, and then these are all the parking places, and actually how you turn in from this road and come into the parking lot. And let's see, the other thing on this one, I think there's actually a detention pond on this, because the water that flows off of this is going to run downhill in this direction right here, and from there it will go into the storm sewer system. So here's a civil engineering drawing showing the lots for a subdivision. This is actually a drawing showing storm sewers, and so when you see the water going into the gutter on the side, in this case if the gutter is right down here, this gives you an example of how the water coming in at the top here, going down and going into the storm sewer system, where it can be taken away to where it's treated. This is an example of a mechanical drawing. This one was done using Inventor, and so we have a 3D model of an assembly, and then we have dimensioned views of the parts in the assembly. This is a mechanical drawing that was created using Creo, and this is for the plastic housing for a cordless drill. And in this one, we also see an example of design sketches that were used while the designer was developing what the geometry for this drill would be. This drawing, or actually this is an assembly of quite a few parts. This was all done using SolidWorks, which is a very popular mechanical software. So this is that intelligent 3D model again. This is an intelligent 3D model. We create a 3D model using Inventor, and from that model we can pull a front view, a side view, a back view, and a bottom view. And to those views we can add all of the dimensional information necessary to manufacture this crankcase. Here are the technical drawings of also a plastic drill assembly. And so you can see we're going from the 3D model to a dimension view. Now this is an example of a software called MasterCam, which you can use to create the geometry that will drive a CNC mill or lathe. And so what's happening here, we're going directly from our 3D design to cutting this actual watch case out on a CNC machine. In this example right here, we have a small engine and it uses some springs in it. And so the designer has designed a spring, but actually what they're showing here is that by using Inventor and other programs like that, you can create sort of a prototype of a spring, and then all you need to do is come in and change the number of coils and the thickness of the coil and things like that, and the program will automatically build those customized springs for you. And here we have a really nice, what we would call an exploded assembly and a parts list for a complicated gear assembly. And it's a really nice drawing. And then here are some details of that assembly that include dimensions and the views necessary to make some of the parts of that gear case. This drawing shows what the art for an integrated circuit looks like, and this is done using a CAD program called Cadence Virtuoso. And so the drafter is working from a schematic that's provided by an electrical engineer to get to this design over here, which is actually like a microscopic stencil for making the integrated circuit. And this could be something that might be in your phone or just about anything nowadays. This is a sample of the drawing involved for a printed circuit board. And if you've ever opened up a phone or a computer, you've probably seen the green plastic boards that have the integrated circuits attached to them. The integrated circuits are usually black plastic rectangular things that are soldered onto the board. So this is the artwork for the board, and then we can see where the integrated circuits will be attached to the board. And then this is just a schematic that was generated using a software called AutoCAD, and this is actually also a smart schematic in that if we put an input into this system somewhere, the computer can actually model the signal as it goes through the computer and tell the electrical engineer if things are wired up correctly and if they're getting the desired outputs and things like that. So AutoCAD is what we call a schematic capture CAD program. All right, so how do drafters know what to draw? Well, usually you have a designer. And in this example right here, we have a sketch made by an architectural designer showing a view of a foundation for a house. And they put in their notes and they sketch in dimensions and things like that. They give that to a drafter. The drafter, who's been trained in CAD and in how to create views and how to put dimensions in and notations and things like that, goes from this sketch to creating a CAD drawing. And this is what will go out to the field to the guys that are going to make this foundation. Here's another example of that, where we have a mechanical designer sketch, and it has all the dimensions for all the features on this part, including what the material is. In this case, it's aluminum 6061, which is an alloy of aluminum. When the drafter's finished with that, from looking at this sketch and translating it into a technical drawing, we may have a front view with dimensions of this object right here. So we're looking in this direction right here. And we have a top view with dimensions, and we have a right side view. And so just like I showed earlier, where we have a projection plane out here and you project to this projection plane, and we have a projection plane here, we project out to this, and that's what gives us this view and this view. And then we have a projection plane on the top. We project up, we project the view up to the top, and that's how we get the view that we see here. Technical drawings require us to have an understanding of precise measurement. So on the screen is what's called a engineer scale. And in the engineer scale, we might read from 0 to 1.5 inches. So each mark on this that we see right here is 1/10 of an inch. So when we go from 0 to 1, we're at 1 inch right here, and there's 1/10, 2/10, 3, 4, 5/10. And so 1.5 inches is actually 1 5/10 inches. We can do the same thing for 2.75. So we go to 2 inches, we count 7/10, and then the 5/100ths here would be halfway between the 7th and 8th tenths. All right. Now we can actually go all the way to tenths, hundredths, and thousandths of an inch. And so that's what we see right here with 3.125. And so in this course, we'll get into things like that, about what we call the precision of dimensions and how many decimal places we may take something to. The metric system is the international standard of measurement. In this course, we will get into that. And so this is a metric scale that we're looking at right here. And so we can read that as that each of these marks on this is 1 millimeter. And so when we get to out here where it says 3, if we count each of those marks, we're actually at 30 millimeters. When we get to 4 and 2 more marks, we're at 42 millimeters. We'll get more into this in the course. And of course, when we draw with CAD, we will be using the same types of measurements. So we'll either use inches, which we call the British imperial system, or we'll use the metric system, and in this case, we'll use millimeters. If you were making a map, you might use meters and feet rather than inches and millimeters. Did you know that 1 inch equals 25.4 millimeters? In this slide, I wanted to show you sort of the way that designers letter or write. It's sort of a tradition among designers that they don't letter like normal people do. They have a sort of a stylized architectural or mechanical look to their lettering, and this is developed only through practice. And so in this course, a lot of times, and other technical drawing courses, your instructor will sort of emphasize that when you're making a sketch, that you need to pay attention to the way you write. And so there's some opportunities in this course to work on your lettering skills. So I wanted to point that out to you. Career paths in technical drawing include architectural drafters, civil drafters, electrical and electronic drafters, mechanical drafters, pipeline drafters and process piping drafters. There's aerospace drafters. There's all sorts, and that's partly why I wanted to show you all those drawings a minute ago, to help give you an idea of what these different disciplines look like. In each case, you would need to get training in these areas. So most people get their training at a community college or a technical school program that may lead to a certificate or an associate's degree in drafting or design or computer-aided design. These programs are usually 1 to 2 years in length, and they usually include teaching you drafting techniques, drafting standards, dimensioning practices, things like that, and how CAD programs are used to create drawings. Most drafters are employed by architectural and engineering firms, and typically they'll work a 40-hour week, and usually will qualify for overtime when they work more than 40 hours. Some drafters work as contractors, so they're like sort of free agents, but contractors are usually very experienced drafters, and they earn high salaries, but they're considered to be an expert. So most of the time, people don't begin as a contract drafter. Most people will work directly for an organization when they come out of school. Occasionally, an organization will allow drafters to work from home and to transfer their drawing files to the office via the internet. Designers are often former drafters who have worked their way up through experience to where they can design things and give them to drafters to be drawn. And a designer may also supervise a group of drafters. Designers usually have a higher salary than a drafter, so a designer is a good career path for a drafter to advance into. The other problem with being a designer, though, or why you make more money, is that you have more responsibility, and so it's probably a little higher stress job. Some drafters want to become architects and engineers, or they just want to become an engineer and architect right off the bat and just use these drafting tools. And in order to do that, you're almost certainly going to have to earn a bachelor's degree in engineering or architecture from a university program. And these bachelor degree programs generally take 4 to 5 years to complete. So if you're interested in that, you should look at the universities that you're interested in and find out what the requirements are, what the course is, how long it takes, and how you can get admitted to a program like that. After earning their degree, an engineer can become a professional engineer, or what we call a PE, and an architect can become licensed through a process that involves both work experience and passing some very strenuous professional exams. So you can go out onto the internet and you can find out more about that process. Most states have a process for becoming licensed or becoming a professional engineer. Qualities that employers look for in drafters. So employers are really careful in making these hiring decisions, and interviews can be very thorough and can last a long time. And sometimes they may ask you back for more than one interview, and when you interview for the job, you might interview with only one person, or you might have to interview with a whole design team. Often, the employer is going to require you to sit down at a computer and take some kind of a CAD test or drawing test, and they may give you something to draw and give you a time limit on it, so you should expect to have to do that. You know, they're trying to determine your attitude and how well you're going to fit into the team and how soon you're going to contribute. So those are things to keep in mind when you go to your interview. So they're looking to try to answer the questions in the interview, like, are you a quick learner? Are you intelligent? Will you fit into the team? Did you make good grades in your major when you were in college? Did you meet your deadlines? Did you work successfully with other people and in groups? Are you prepared by your training to do the job? Do you communicate well? Do you have good work habits? Are you dependable? And really the ultimate is, can the employer profit from your efforts? So how do you think that they might go about figuring this stuff out? Well, after the interview, more than likely they're going to ask you to provide them with some references. And good references can come from your college teachers. So I think it's important that you make a good impression on your college teachers, that you come to class prepared and on time, that you meet your deadlines, that you hand in good work, that you have high standards, those sorts of things, so that when you ask one of your professors to be a reference, that they won't have any reservations in doing that. Salary information for drafters. This is from the U.S. Department of Labor in 2018. These are the latest statistics I could find. Showed that the median income for architectural and civil drafters in 2018 was $54,920. Mechanical drafters made a little bit more, $55,920, and electrical and electronic drafters made the highest at $60,000. Now, this is going to vary on which part of the country you're in and how much demand there is for drafters. And so, in a very good job market, in a town that's thriving and growing really fast, even beginner drafters may begin in the $50,000 range. Most of the employers I see offer somewhere between $40,000 to $50,000 for students graduating with an associate degree. By comparison, the median earnings for an architect are about $79,000, for a mechanical engineer about $87,000, for civil engineers about $86,640, and electrical engineers almost $100,000. And median means that half of the people they surveyed made more than that and half made less than that. So this is not an average. These are the medians. So it's sort of that middle point between the really high salaries and the lower salaries. And like I said, all of this was taken from the Bureau of Labor Statistics, and you can go online at the U.S. government's website, Bureau of Labor Statistics, and you can find out all kinds of information about jobs in drafting and engineering and architecture. According to the Department of Labor, there are around 200,000 Americans employed as drafters, with a projected growth of about 22,000 more drafters by 2026. And so that's not that far away. And in the area where we are, which is Austin, Texas, the growth of drafters, it's just been like a weekly occurrence of companies contacting us to hire drafters. in summary, the curriculum of this course is designed to introduce you to the field of technical drawing, and it's a good way to explore whether or not you possess the interest and aptitudes necessary to pursue a career in technical drawing. If you wish to pursue more training following this course, most community colleges and many universities offer advanced, specialized courses in engineering and architectural drawing, and your instructor may be able to advise you on opportunities to get more training or possible career paths. So feel free to ask your professor about that.